Quantum Darwinism
In the vast and mysterious realm of science, people always strive with all their might to prove each hypothesis in a solid and reliable way, but just because something remains beyond our current ability to observe it directly and has not yet been clearly demonstrated does not mean that it does not truly exist in reality. Picture yourself standing in the middle of an immense ocean on a dark night, with waves gently lapping all around you, a chilly wind brushing through your hair, and the pitch-black sky overhead dotted only with a few faint twinkling stars. You might wonder what profound secrets could be hiding beneath that shadowy layer of water, secrets that humanity has never yet touched or explored. This is exactly how scientists feel about the universe, an enormous expanse filled with countless strange and wonderful possibilities that stretch the imagination. Take black holes as a prime example. These are gigantic entities that swallow everything in their path, including light itself, which makes anyone shudder when contemplating their terrifying pulling power. Carl Schwarzschild, a brilliant physicist, recognized the potential existence of black holes right within the framework of Albert Einstein's general theory of relativity, which Einstein published in 1916. Schwarzschild made this insight while sitting in his quiet study room, surrounded by scattered papers and pens, carefully working through complex equations under the soft glow of a dim lamp. Even earlier than that, John Michell, an English scientist from the 18th century, used Newtonian mechanics to hypothesize about the existence of these dark stars as far back as 1783. He came to this idea while peering at the night sky through a rudimentary telescope, envisioning objects from which light could not escape due to their immense gravity. This means that for 55 years after the general theory of relativity was introduced, or even 188 years if counting from Newton's era, scientists had been aware of the theoretical possibility of black holes. However, they had never actually seen one with the naked eye or through any telescope. They could only dream about them through mathematical formulas, feeling as if they held a cosmic secret in their hands but lacked the key to unlock it fully. It was not until 1971 that the first black hole, named Cygnus X1, was observed and confirmed with certainty. Astronomers detected a fierce hiss from an X-ray source in space, much like a distant roar echoing from the deepest heart of the universe. And now, with the first ever image of a black hole captured by the Event Horizon Telescope project in 2019, showing a glowing orange ring surrounding the endless darkness of the black hole in the galaxy M87, and more recently a sharper image of the black hole Sagittarius A* at the center of our Milky Way galaxy in 2022, people have visual evidence that makes hearts beat faster with excitement and wonder. There is nothing too unbelievable about similar things happening again, with fresh discoveries that leave everyone astonished and open-mouthed in awe. In the endless ocean of scientific possibilities, where strange ideas pile up on one another like rising waves in a swelling tide, there could exist bizarre stars and unusual forms of matter that popular theories predict but which have not yet been seen directly. Nobody knows for sure what these objects are. They lurk somewhere in the cosmic darkness, waiting for human technology to advance further so they can reveal themselves. That is why they have not been proven yet, but this only adds to the thrill, like awaiting the arrival of a massive storm on the horizon. But the speaker has some interesting ideas to share. The speaker is Alex McColgan, and you are listening to the program Astrum, where people explore the mysteries of the universe through honest storytelling, as if sitting around a campfire under a sparkling starry sky. In this video, viewers will look back at the strangest forms of objects or states in the universe, things that could be real if one of them is found to prove it, making the viewing room atmosphere tense and full of excitement. Check back in another 188 years to see how many of those things have become reality, or perhaps this video will become outdated much sooner than anyone thinks, as new telescopes like the James Webb Space Telescope continue to send back stunning images from 2021 onward, revealing more about the early universe and its hidden wonders. It is no surprise that astronomers first turn their gaze towards stars, those enormous balls of fire shining brightly in the night sky, making people feel tiny when looking up at them. Stars are among the most radiant and majestic objects in the universe, with their blinding light piercing through the cold void of space, illuminating the dark night sky and warming the planets around them like a gentle mother embracing her children. Through intense nuclear fusion reactions deep inside their cores, they release huge amounts of light, acting like ceaseless cosmic forges, and through violent mergers or brilliant supernova explosions, stars are also responsible for creating heavier elements such as iron and gold, which make up much of the matter around everyone, from the planet people stand on to their own bodies. Astronomers and astrophysicists have come a long way in understanding how stars work, from initial observations with simple telescopes to complex computer models today, to the point where people can even predict when the sun will run out of fuel and swell into a red giant in about 5 billion years, making Earth unbearably hot and uninhabitable. But today the discussion is not just about the familiar types of stars seen every night. Instead, people will reflect on stars that humanity has never seen, theoretical entities that keep scientists awake at night pondering. These are stars that astrophysicists believe could exist in theory, including stars made from vacuum itself, an idea that sounds like something from science fiction novels but has solid mathematical foundations. First, a foundation needs to be laid by understanding how stars function, starting with the most important star for everyone, the Sun, that fiery plasma sphere which rises on the horizon every morning, bringing warmth and light. Since the Sun is made of gas or plasma rather than solid matter, nobody could stand on its surface like on Earth without being swallowed instantly. The enormous gravity would pull a person straight down to the center at dizzying speed, like falling into a bottomless abyss. So why does the gas layer on the Sun's surface not get sucked into the core, yet maintain a perfectly round and stable shape over billions of years? It turns out there is pressure from the Sun's core pushing outward, perfectly balancing that gravity, creating a harmonious equilibrium that allows the Sun to endure for so long. The main source of this pressure is radiation generated from nuclear fusion reactions in the core, where hydrogen fuses into helium in non-stop microexplosions, and this same radiation carries light and heat from the Sun to Earth, letting people feel gentle warmth on their skin. Whether radiation is thought of as individual photons speeding through space or as oscillations in the electromagnetic field, as they travel from the core to the outer layers of the Sun, they create an outward push in all directions, like a strong wind from inside inflating a gigantic balloon. This radiation pressure is not strong enough to stop someone from falling into the Sun if they suddenly appeared nearby, but it is sufficient to prevent the Sun's own light and easily compressible gas from collapsing inward, keeping the star vibrant and alive. This balance between gravity pulling in and pressure pushing out is a common feature of nearly all known types of stars, a delicate cosmic dance where two opposing forces hold each other in perfect equilibrium, much like two wrestlers locked in a stalemate on the mat. What distinguishes different types of stars is the source of that pressure, giving each star its own unique character. For the Sun, the pressure comes from fusing hydrogen into helium, a process continuously happening in its core at millions of degrees. When the Sun runs out of hydrogen in about 5 billion years, it will expand into a red giant, its surface swelling to engulf inner planets, and start generating pressure by fusing helium into heavier nuclei like carbon and oxygen, in a dramatic final life stage. Eventually, the Sun will exhaust helium and all light elements usable as nuclear fusion fuel, then shrink into a small star called a white dwarf, a faint remnant compared to its former glory. Since no nuclear fusion occurs anymore, white dwarfs are sometimes called stellar remnants rather than true stars, but they still emit weak light from leftover heat, like glowing embers after a great fire. But without fusion, what pressure keeps this remnant from collapsing under its own weight? It turns out gravity squeezes the white dwarf's gas until it becomes extremely dense, with density so high that a teaspoon of its material weighs as much as a mountain, and a new type of pressure emerges called electron degeneracy pressure. This is a pure quantum mechanical effect, where electrons are packed so tightly that they resist getting any closer, similar to why a hand cannot pass through a solid object without strong resistance, because electrons in atoms refuse to be forced together. However, there are stellar remnants so massive that even electron degeneracy pressure is not enough to counteract gravity, leading to a limit called the Chandrasekhar limit, where no stable white dwarf can exist with mass greater than 1.4 times the Sun's mass, a figure calculated by Subrahmanyam Chandrasekhar in the 1930s when he was young, during a ship voyage from India to England. If a star has burned all its nuclear fuel and its core is still heavier than the Chandrasekhar limit, that core will continue collapsing until it becomes dense enough to form an even stronger quantum pressure called neutron degeneracy pressure, preventing neutrons from getting too close, creating a superdense neutron sphere. A star reaching this state is called a neutron star, the smallest and densest known stars in the universe, with a diameter of only about 20 kilometers but mass twice that of the Sun, spinning wildly at hundreds of revolutions per second, emitting beams like a cosmic lighthouse. So is there a maximum mass limit for neutron stars? Yes, that limit is around 2.2 times the Sun's mass, based on modern models. If heavier, the neutron star will keep collapsing under its own gravity until nothing remains, because neutron degeneracy pressure is the strongest that ordinary matter can produce, with nothing left to stop that heavy remnant from collapsing forever. This is the fate of the largest stars in the universe. From an outside perspective, they become so dense that all anyone sees is a black hole, a region of space where time stops and everything vanishes into eternal darkness. That is a terrifying level of pressure, making anyone empathize with those stellar remnants. Perhaps it is time for them to find a less demanding job, such as software programming, where someone sits in an air-conditioned room typing code without worrying about being crushed by gravity. And yes, learning that profession can actually be quite enjoyable thanks to the sponsor of this video. Boot.dev is not an ordinary programming course. Their website is designed like a fantasy adventure game with quests and interactive elements, making users feel like exploring a new world, completing tasks to learn coding, with cheerful background music and rewards that make the process engaging. In the end, users complete real projects that build genuine skills applicable to actual jobs. If difficulties arise, their community is always ready to help through lively forums, or users can chat with Bear AI. And yes, it really knows how to write code quite well, responding quickly like a companion. The first chapters are free to try, then all content can still be read for free, and using the CoderStrum gives 25% off the first payment, an offer that brings a smile when starting the journey. Returning to the main topic, the atmosphere in research rooms becomes lively as scientists begin wondering what would happen if a star were not made of ordinary matter but of more exotic forms. If exotic matter types could produce pressure greater than neutron degeneracy pressure, what new kinds of stars could exist, opening a new horizon full of surprises? Someone might think people just need to follow the previous pattern, with stars getting smaller and denser than neutron stars, as long as there is a stronger pressure to resist gravity, like building a taller tower with a sturdier foundation. Someone might think the ultimate limit is only when the star becomes smaller than its own Schwarzschild radius, the point of no return where it becomes a black hole. That is close but not quite, because there are subtle nuances. Physicist Hans Bethe and colleagues in the 1950s showed that a star made of any realistic matter, meaning with positive energy density and pressure, cannot be smaller than about 9/8 of its own Schwarzschild radius, a factor that makes the size difference significant. It sounds like not much variation, but that 9/8 factor means any real star must be considerably larger than a black hole, making it easier to distinguish between the two through observations. And then physicists started asking about stars that could be called less realistic, opening the door to wild ideas. For example, what if a star were made of matter that could have negative pressure in some regions and positive in others, creating interesting instability? Then the Bechdel limit no longer applies, and the star could be smaller than 9/8 of the Schwarzschild radius, even almost the size of a black hole with the same mass, making them perfect imposters. Such theoretical stars that mimic black holes have become a nuisance for astrophysicists, because every time they detect an object that looks like a black hole through gravitational waves or X-rays, they cannot be certain it is a black hole and must say it is either a black hole or an extremely dense object imitating one, making debates at scientific conferences heated. Though in their hearts most believe it is a real black hole, based on data from LIGO and Virgo detecting dozens of black hole mergers from 2015 to now. Back to the main question, what would those exotic stars with negative pressure look like, hovering in dark space? The answer is stranger than imagined, making anyone feel dizzy. Tolman, Oppenheimer, and Volkoff in the 1930s derived an equation describing how pressure in a stable star changes from the center outward, now called the Tolman-Oppenheimer-Volkoff equation, a complex but elegant formula. If the star's center has strong negative pressure, meaning it creates a pulling force instead of pushing, the TOV equation shows the star can only be stable if its pressure varies in an extraordinarily unusual way, like a chaotic symphony. First, pressure must drop to negative infinity at some point inside the star, then switch to positive infinity and gradually decrease outward until reaching zero, marking the star's surface boundary, a structure that amazes mathematicians. The exact location where pressure reaches infinity depends on the central pressure value, so by adjusting the central pressure just right, pressure can be kept finite all the way to the star's edge, avoiding uncomfortable infinities. This happens when the pressure at the star's center is exactly equal and opposite to the energy density at that point. In this special case, the TOV equations show that pressure and energy density remain constant, balanced and opposing each other throughout the star's volume right to its surface, a quirky harmony. If some previous episodes have been watched, this might seem familiar, reminiscent of mysterious concepts. A constant positive energy density combined with constant negative pressure sounds unlike any star ever seen, but it starts resembling a mysterious component of the universe, dark energy, which is pushing the universe to expand at an accelerating rate. And since pressure and energy density in a gravastar have equal magnitude, it is not just any dark energy but the characteristic of vacuum energy, the cosmological constant that Einstein once called his biggest blunder. That is why this special and strange star is called a gravity vacuum star, or shortened to Gravastar, an idea proposed by Powell Mazer and Emil Motola in 2001, and still researched today. Inside a gravastar, gravity is zero because positive energy and negative pressure create two pulling and pushing forces that balance each other, like being inside a perfectly balanced ball. And since pressure in a gravastar is constant, there is no pressure gradient to create any directional push, meaning if someone were inside a gravastar, they would not be pulled in or pushed out. They would float freely as if in true vacuum, no gravity, no direction, just strange peace amid the chaotic universe. Another odd feature of stars with negative pressure is that the closer they get to the special gravastar limit, where infinite pressure surface is pushed to the star's edge, the closer their size gets to that of a black hole with the same mass, making them almost indistinguishable from afar. This raises two big questions attracting much attention from physicists, with new papers constantly published. First, how can people know if the superdense objects astronomers observe in mergers or at galaxy centers are real black holes or just strange stars of similar size, especially with data from LIGO, Virgo, and Kagra detecting gravitational waves from 2015? Second, if gravastars really exist and are distributed throughout the universe, could they be the dark energy that has been accelerating universe expansion over the past 5 billion years, based on 2024 observations from Planck and Deci showing dark energy might be slightly changing? To answer the first question, physicists rely on the fundamental difference between black holes and other dense objects, which is the existence of an event horizon, an invisible boundary from which nothing escapes. The defining feature of a black hole is that nothing, once fallen inside or even touching its surface, can escape, not even light, creating absolute darkness. In contrast, if a strange star is only slightly larger than its Schwarzschild radius, it would have no event horizon, and in theory could emit information outward as light or waves, though faintly. Not only that, objects without event horizons could produce different gravitational wave signals from black holes during mergers, with characteristic echoes, allowing distinction by measuring and analyzing gravitational waves with observatories like LIGO, which has detected over 90 events from 2015 to 2025. But even with these advanced testing methods, stars small and dense enough remain very hard to distinguish from black holes, requiring more precise data. So far, the best that can be confirmed is that the radius of observed black hole candidates in the universe is at least approximately their Schwarzschild radius, in some cases rough estimates, but in others scientists have calculated it precisely to 40 decimal places through gravitational wave modeling. Regarding the second question about dark energy, things get much more interesting, with new studies from 2023. In early 2023, a physics group at the University of Hawaii published analysis showing astronomical observations of massive black holes indicate they increase in mass over time, exactly matching the rate dark energy is predicted to increase due to universe expansion, based on data from Chandra and Hubble. They concluded black holes must be made of dark energy and are actually more like gravastars than ordinary black holes with infinite density singularities at the center, a bold idea. This conclusion sparked intense controversy, with astronomers objecting that observational data analysis is inaccurate while theoretical physicists argue universe expansion has nothing to do with black hole growth, and 2024 studies from DESI show dark energy may not be completely constant. So although the idea that dark energy could exist as gravastars sounds appealing, the scientific community is not convinced unless more precise data and solid theoretical models come from future missions like Euclid or Roman Space Telescope. In other words, even if gravastars could exist, people are still far from proving it, and they might look too much like black holes to recognize easily, making the exploration journey full of challenges. But the next strange object to discuss is completely different, almost opposite to black holes. If black holes are swallowing pulls, these are erupting pushes. These are white holes, and there is no physical reason they cannot exist, though they might be unstable. Start with a simple comparison for easy visualization, like sitting at a coffee table telling stories. If told to imagine a cone, someone might think of an upward-pointing cone like a traffic pylon on a busy street, or a downward-pointing cone like an ice cream cone held in hand. Those are common real-world examples, familiar and tangible. But if the mathematical equation for a cone is written and drawn on paper, a shape like two cones joined at the tip emerges, a perfectly symmetrical structure. In mathematics, a cone has two halves, one pointing up and one down, connected at the apex, spanning two dimensions. The cones seen in everyday life are just cut-out portions of that full mathematical cone, like taking only part of a bigger picture. Black holes are similar, only one half of the mathematical solution. Many black holes in the universe are remnants of massive stars collapsing under their own extreme gravity, a dramatic process with a bright supernova explosion before darkness takes over. When a black hole forms, it completely separates from the rest of the universe by a spherical boundary called the event horizon, where time slows and space warps. Everything can fall in but nothing, not even light, can escape, creating deadly silence. This spacetime structure can be neatly represented in a diagram called the Penrose diagram, allowing the entire infinite spacetime to be described in a finite drawing, with smooth curves under the desk lamp of Roy Penrose when he developed it in the 1960s. The key feature of this diagram is that light always travels at 45-degree angles, making it easy to identify regions where light can enter and where it cannot, like a treasure map. In the diagram, Region 1 is the normal universe, containing the initial star before collapsing into a black hole along with everything else from infinite past to infinite future, with galaxies swirling. Region 2 is the black hole, separated from the rest by the event horizon. Light can easily enter Region 2 but cannot escape, eventually hitting the singularity with infinite density. The same applies to ordinary matter, which moves slower than light, so in the diagram it can only go upward at angles greater than 45 degrees, slowly but unable to turn back. The special aspect of the Penrose diagram is that it describes black hole formation at a specific moment when the star collapses into itself, with echoing explosions in space. In the distant past, there was no black hole or event horizon, and light could move freely everywhere, as free as the wind. But this diagram only represents the type of black hole commonly seen in reality. It is just the ice cream cone half in the full picture of general relativity. So if ignoring the real world and imagining an ideal black hole with infinite past unrelated to star collapse or matter, what happens, opening new possibilities? The full mathematical cone corresponding to that black hole looks like what? It could be a simple extension of the original Penrose diagram, but the physics inside is completely reversed, like looking in a mirror. Region 1 remains our universe, Region 2 the black hole with singularity in the future. But mathematics also reveals a third region, like the inverted image of the black hole, where everything flows backward. In this region, instead of the singularity in the future, it is in the past. If light paths are drawn at 45 degrees, light can easily leave region 3 but cannot enter, like a gushing fountain. This type of region is a white hole, similar to the traffic cone in the earlier example, pushing everything outward with powerful force. But it does not stop there. On the other side of the white hole is another spacetime region marked as region 4, connected to the black hole and white hole in the middle, just like the connection between the normal universe and them, creating poetic symmetry. Region 4 is a completely separate parallel universe from ours because even light cannot transfer between the two regions, like two distinct worlds. In other words, the same mathematical equation describing the normal universe and black hole also describes the parallel universe and white hole, an elegance of mathematics. This does not mean every black hole is connected to a white hole. Just like in the cone example, reality only contains cut-out pieces of the full mathematical solution. But it does mean that even if white holes are rarer than black holes or even none exist in our universe, they are completely consistent with physical laws, violating nothing. In the example, if imagining ice cream cones remain common but traffic pylons become rare and disappear, that does not make the concept of traffic pylons unrealistic. The status of white holes in current physics is similar, theoretically reasonable but without direct evidence. In theory, they are fully valid, but perhaps white holes that existed in the early universe were unstable and vanished quickly, like soap bubbles popping. If wondering whether more stable, tiny white holes that have not been discovered exist, many scientists ponder that at night. And continue following because the discussion is about to cover the smallest possible white holes, with new theories from quantum gravity. But first prepare because the Penrose diagram not only describes white holes but can open a whole new level of bent spacetime, full of color and surprise. That is the world of wormholes and parallel universes, where reality surpasses imagination. The no-hair theorem states that a black hole can have at most 3 intrinsic properties: mass, electric charge, and spin, like a simple ball with only size, color, and rotation speed. However, the Penrose diagram just presented only describes the simplest type of black hole, without charge and completely stationary, like a silent sphere. Diagrams for charged or spinning black holes are much more complex but also far more interesting because they completely change how the singularity is understood, while opening new spacetime regions full of appeal, making anyone feel lost in a maze. Take the Penrose diagram of a spinning black hole as an example, with Roy Kerr solving the equation in 1963. Instead of just 4 separate spacetime regions, now there are up to 8 regions repeating in an infinite pattern of parallel universes, an intricate network. Regions 1 to 4 remain as before: normal universe, black hole, white hole, and parallel universe. But when the black hole starts spinning, its geometric structure no longer has an unavoidable singularity in the future, and similarly, the white hole loses its past singularity, opening new paths. So what really happens when crossing the event horizon of a spinning black hole, imagining being a brave astronaut? At first pulled toward the center as expected, with increasing pull, but eventually crossing a boundary called the Cauchy horizon, where time structure stops bending, allowing stopping and not falling deeper, an unexpected stable region. In the deepest areas marked as regions 5 and 7, free floating is possible, approaching or moving away from the center, even touching the singularity if desired, though not recommended due to deadly danger. In this curved and spinning space region, one is actually inside a wormhole, a tunnel connecting spaces. If not for being completely separated from those still in region 1, this would be the perfect time to boast about the crazy spacetime adventure via radio. Here a fork in the road appears, a fateful choice. One choice is to continue deeper, circling the singularity, which for spinning black holes is a ring rather than a point. That path leads to region 6 or 8 in the diagram. However, this path's existence is likely a flaw in general relativity's prediction rather than reality, because circling the singularity once could lead to causality paradoxes, where returning to one's own past and changing history is possible. the safer choice is to turn back and move outward, crossing the Cauchy horizon just entered, which leads to Region 3, a white hole, ejecting at terrifying speed into a completely new universe similar in structure to the starting point, but unfortunately without friends or family waiting, only loneliness in unfamiliar space. In reality, upon arrival, the old universe has passed an infinite amount of time. One would live in an entirely new definition of the future, with time stretched. Now return to reality, leaving theoretical dreams. Though traveling through a wormhole sounds exciting in theory, survival in practice is almost certainly impossible due to tidal forces tearing the body apart, and even likely the wormhole itself would collapse upon disturbing its spacetime structure with presence. So which part of this mathematical model could really exist in the actual world, under observational light? Spinning black holes with event horizons seem to appear everywhere in the universe, with evidence from quasars and gravitational waves. But what happens inside them remains almost completely unknown, a dark secret. There are two main reasons the physics inside real black holes may differ from Penrose diagram descriptions. First, when black holes form from chaotic collapse of massive stars, some assumptions used to create the Penrose diagram break, such as assuming the black hole exists forever or the surrounding universe is perfectly symmetrical without random objects falling in, like people or asteroids. Second, general relativity itself, the foundation for the Penrose diagram, may only be an approximation and breaks down near the singularity where spacetime curvature becomes extreme, requiring a quantum gravity theory. So it is highly likely that some diagram predictions, especially those involving singularities and time travel paradoxes, are not real features of strongly curved spacetime. However, white hole existence remains an open possibility, leaving room for speculation on how they form and whether they leave observable traces, perhaps through unusual gamma-ray bursts. A recent hypothesis gaining attention is a white hole born when a black hole dies, and no, this is not a mystical story of rebirth or magic, but a real effort to understand the full black hole life cycle with clear mathematical basis from Stephen Hawking. Even an isolated black hole in empty space continuously emits particles called Hawking radiation, gradually shrinking and losing mass over time, a slow but unstoppable process. But when a black hole reaches extremely small mass, the Planck mass of about 20 micrograms, what happens next cannot be predicted without a complete quantum gravity theory. This is where loop quantum gravity theory comes in, an effort to connect gravity with quantum mechanics, where space consists of discrete loops like a crystal network. In short, this theory's equations predict that instead of continuing to shrink below Planck mass, the tiny black hole could quantum phase transition into a white hole, spewing back all internal matter to the universe over a long time, like a small but intense explosion. The miracle is that though this white hole is also small and light, it can still hold enormous entropy because its internal structure has been stretched into a thin tube with huge volume, a treasure trove of information. This entropy reserve could enable recovering all information ever fallen into the black hole in the distant future, solving the decades-long theoretical physics puzzle, the information paradox, where information seems to disappear violating quantum laws. As the white hole releases this information, it gradually fades and vanishes, surrounding spacetime loses tension, and its life cycle closes peacefully. In general relativity, the entire universe is thought to have had a singularity in the past about 14 billion years ago at the Big Bang moment, a bright event starting everything. In that way, our universe resembles a static uncharged white hole, erupting matter and energy. But if loop quantum gravity says white holes can be born when black holes collapse, does the same apply to the universe's birth itself? Could this expanding universe have been born from the remnants of an ancient contracting spacetime, an eternal cycle? It sounds crazy, but this theory says it is entirely possible, with bounce cosmology models discussed in 2025. So perhaps the concept of white holes is not as far-fetched as thought. Maybe it is time to believe in white hole existence, because in a way, people might be inside a gigantic white hole, the universe itself being that eruption. Thus, white holes could fully exist in the real world, though not yet observed certainly, but there is another detail in the Penrose diagram that might make eyebrows raise. which is that the diagram refers to parallel universes, a grand claim. Could complete universes exist that are inaccessible but run parallel beside ours, with separate lives? There are some reasonable reasons to believe that could be true, but before getting there, attention needs to turn to a baffling cosmic mystery and the worst prediction in physics history, which Einstein regretted. It starts with a seemingly simple question: why is our universe expanding, with distant galaxies moving away like friends parting? One of the first things learned in physics class is that gravity is an attractive force between two objects proportional to their masses, a classical rule from Newton. Gravity keeps planets orbiting the Sun in regular paths, holds stars together in the sparkling Milky Way, and binds galaxies into clusters and superclusters, creating the universe's structure like a gigantic spider web. But when looking farther out, this gravity seems to work in reverse, accelerating clusters of galaxies apart instead of pulling them closer, a phenomenon discovered by Edwin Hubble in 1929 through redshift. So what is happening, making space breathe out? Einstein's general relativity provides a lens to understand this strange phenomenon, where space is not just a background for object movement but space itself can expand, curve, and evolve over time, like an elastic fabric. Einstein showed that in this framework, gravity is no longer a force but the curving of inertial paths in dynamic spacetime, elegant and profound. For example, when a planet orbits the Sun in Einstein's view, it just follows a straight line in curved space, without needing an invisible pulling force. This means what is observed as a pushing force between galaxy clusters is actually the accelerating expansion of space between them, with speed measured through Type Ia supernovae in 1998. But what could cause this expansion to accelerate on a universe-wide scale, opposing gravity? To answer, understand what makes spacetime expand and curve in the first place. In Newtonian mechanics, every object with mass creates attractive gravity. In general relativity, every object with mass curves spacetime around it. Einstein also showed that besides mass, any form of energy or pressure affects spacetime motion. Energy density is the amount of energy in a volume of space, including heat, motion, radiation, and in our universe it is always positive. Pressure is the force that matter in that space exerts outward, for example interstellar dust lightly colliding in cold cosmic voids. For widely separated objects, this pressure value is nearly zero on universe scales. When the sum of these two is positive as in the formula, their effect makes surrounding space contract, in other words, they create gravity, slowing expansion. However, suppose somehow pressure becomes negative and larger than positive energy density, the minus sign in the formula reverses the entire effect, resulting in accelerating space expansion and antigravity. In other words, a volume of space containing antigravity or dark energy has been created, occupying about 68% of the universe according to Planck 2018 and DESI 2024 data. It is a rather vague concept because imagining negative pressure is hard. How can there be less than zero particles in a space region? But particles are not the only thing creating pressure. Physical fields can also create pressure, for example a magnetic field pulling an iron piece toward a magnet or pushing same poles apart. If dark energy is a field pushing everything away, not just magnets but matter, light, space, it perfectly matches telescope observations. The universe's vacuum contains dark energy, enough to very gently push the universe wider, with Hubble constant about 70 km per second per megaparsec. Scientists have studied dark energy for many years and calculated the total energy density and pressure needed to produce the space expansion speed seen, that value around 10 to the minus 9 joules per cubic meter, an extremely small number so it is not noticed on Earth but only observable on universe scales through distant galaxy redshift. This is actually good news, because if the number were higher or lower slightly, existence would be destroyed completely. The universe would be too chaotic or collapse. Illustrate this with universe history, from Big Bang to now. This is the full evolution process of the universe from right after the Big Bang to present, with temperature gradually dropping from billions of degrees. This curve represents dark energy density measured by astronomers through supernovae and cosmic microwave background, They believe dark energy's negative pressure has kept this density nearly stable over billions of years, though some new evidence from DESI 2024 shows dark energy weakening slightly over time, a discovery that could change models. But that does not change the key point here. This is ordinary matter density in the universe, which has almost no pressure. This density decreases over time because expanding space dilutes matter inside like thinning coffee. Finally, this is radiation density in the universe, including photons and other ultralight particles. Radiation's positive pressure makes it dilute faster than ordinary matter, dominating the early universe. At the universe's starting moment in an extremely short time, no atoms existed yet, only scorching plasma. Very soon after, protons and neutrons fused to form the first atomic nuclei in the early universe during nucleosynthesis, about 3 minutes after the Big Bang. Not long after matter became the dominant energy form, the universe cooled enough for these nuclei to attract and hold electrons, forming the first hydrogen and helium atoms about 380,000 years later, the recombination event releasing the cosmic microwave background radiation seen today. These atoms are the foundational matter blocks for the first stars, forming about 100 million years later through gravity. Under gravity's effect, stars gathered into the first galaxies and galaxy clusters, observable through James Webb from 2022. Only later did dark energy dominate, starting accelerating space expansion and preventing larger structure formation from about 9 billion years ago. But what would happen if dark energy density were larger? Imagine the tense atmosphere. Imagine if dark energy's push were stronger. It could be strong enough to prevent early galaxy formation, pushing stars apart before gravity could pull them together. The universe would be empty. If a bit larger, star formation would become almost impossible, no element forges. And if dark energy density too large, the universe could hardly produce atoms or even nuclei, everything torn apart from the start. That is what could have happened, a catastrophic scenario. And what should it have been according to theory? Based on clever calculations and quantum field theory principles, scientists tried predicting dark energy density from quantum vacuum, resulting in a value much larger than observed reality. How much larger? The estimate is 10 to the 120th times larger, a gigantic error called the cosmological constant problem. If placing this number on a graph, it would completely exceed all scales. The universe would expand too fast immediately. If that prediction were correct, today's universe would have no structure, no galaxies, no stars, no life, just a vast void full of dark energy tearing everything apart. And if dark energy density were negative 10 to the 120th times, the universe's fate would be no better. It would quickly collapse back into itself in a big crunch, crushing everything. And this is the mystery of why dark energy density is dozens of orders lower than prediction and precisely matches the level needed for life to exist, a fine-tuning that baffles scientists. Scientists try explaining this huge discrepancy with hypotheses that undetected particles with positive energy but negative pressure exist to balance equations and bring dark energy density near zero, like actions or quintessence. There could be a huge potential energy with negative value like a cosmic spring stretched holding back the erupting energy, or our quantum field theory is wrong on large scales. However, with so much experimental evidence supporting quantum field theory from particle accelerators to spectra, completely rejecting it would be unwise. Instead, people must gaze at this universe's miraculous coincidence with awe, feeling small before the scale. What probability makes dark energy density so low, when it should be immensely larger, a number small almost to zero but not zero? How can the universe balance perfectly so people are not torn apart or crushed into a singularity? If this value were not so small, existence would be impossible. Even the first atoms would never combine because expanding space would rip them apart. According to prediction models, people are indeed very lucky. This coincidence happened exactly to allow life to form from cosmic dust. But is it really random coincidence, or something deeper? This problem in modern physics is called the cosmological constant problem, a philosophical as well as scientific question. Those with religious inclinations would say this is not luck but intentional design, A god or transcendent entity arranged dark energy value perfectly for life to emerge, like a meticulously painted picture. Of course, this idea is not accepted by all because a supreme being's existence is hard to prove or disprove, and science relies on data, not faith. So many scientists need another explanation, purely theoretical. That explanation comes from the multiverse concept, a vast idea. In 1987, when dark energy's exact value was not yet measured but known to be extremely small or zero, because otherwise the known universe could not exist. That year, physicist Steven Weinberg published a paper linking the astonishingly small dark energy value to a concept called the anthropic principle in a lively conference atmosphere. The core of this principle says people can only observe universes with conditions suitable for producing observers, like fish only seeing suitable water. If a universe does not roll the lucky dice that way, simply no one is there to notice. In other words, only universes capable of producing life have people to observe and question their existence, a clever argument. Weinberg went further, saying the threshold dark energy density needed for life cannot be lower than that needed for galaxy formation, because without galaxies and stars, how can life form from heavy elements? At that time, observations of ancient quasars showed galaxies started forming only about 1 billion years after the Big Bang, data from Hubble. From that data, Weinberg calculated that for galaxies to form, dark energy density must be smaller than about 10 to 100 times the current observed value. Meaning if life really needs galaxies, the dark energy density necessary for life must be smaller than or equal to this but not negative. Initially he thought if the actual value were much smaller, the cause certainly not just anthropic principle. But in reality modern measurements from supernovae and baryon acoustic oscillations show actual dark energy density about 10 to the minus 9 joules per cubic meter, very close to Weinberg's 1987 prediction. In summary, life and dark energy density have a surprising connection, almost prophesied. However, this overlooks an important fact. Just because people exist in a suitable universe does not mean that existence is inevitable. People could also not exist because the probability for the cosmological constant to have the exact current value is extremely small, smaller than 1 in 10 to the 120th. Could different dark energy values have coincidentally cancelled perfectly to create a life-suitable universe just by luck? Almost impossible. Probability too low. Imagine randomly picking 3 real numbers from -1 to 1 and adding them hoping the absolute total is smaller than 10 to the minus 55, a tiny number. That is nearly impossible, but if allowed to try millions of trillions of times, eventually one lucky time occurs, perhaps taking 10 to the 100 seconds of tries, but any small probability with enough time happens. With similar logic, explain why dark energy density is strangely low. Suppose not just one universe but countless parallel universes, each with random different dark energy value. Only a tiny fraction have value small enough to allow life, and obviously that is where humans find themselves living, because only their observers exist. This explanation needs no coincidence, no fine-tuning, no intelligent hand, just many different universes, a sea of universes. However, the multiverse idea alone is too vague to be a complete scientific theory. It needs mechanism. The question is what type of multiverse? How do they exist? Fortunately, physicists have proposed several concepts, with lively debates. First is temporal multiverse. If familiar with Big Bang and Big Crunch, know there is hypothesis the universe cycles endlessly, born then dies then reborn in cyclic model. If in each cycle physical constants change slightly, for example dark energy density varies, then after countless times surely one universe has our exact value. Of course, this assumption has many uncertainties because whether the universe really collapses in a big crunch is unknown, with entropy increasing. But if it happens and each cycle changes slightly, this is a viable multiverse model, proposed by Paul Stenhardt. Second model is spatial multiverse. Though physical laws seem uniform in observable range through telescopes, there are regions of space far beyond where expanding universe makes light from their never reach, beyond cosmic horizon. Possibly in those regions physical laws differ completely. If so, Each region can be viewed as separate universe, eternal inflation multiverse from Andre Linde. However, this model seems less convincing because calling an unobservable distant region another universe sounds forced, plus no evidence physical laws change with space. Finally, modern physics describes a third multiverse type, completely separate from our spacetime, according to many worlds' interpretation of quantum mechanics from Hugh Everett in 1957. Each quantum measurement or interaction causes the universe's wave function to branch into many, each branch an independent universe not interacting. If heard of Schrödinger's cat, imagine universe splitting into two, one where cat lives and one where dies, with every possibility happening in parallel. With each interaction, universe count increases exponentially, creating an ever richer quantum multiverse, endless. Of course, whether this branching really reflects quantum mechanics' nature is unknown, but it is the simplest interpretation fully consistent with all experimental data, or at least no evidence refutes it, from double-slit experiments to entanglement. If true, it opens a whole new layer of meaning in understanding multiverse and own existence, every choice creating new worlds. Multiverse is a useful concept because it eliminates need to rely on huge coincidences or intelligent design to explain presence in this universe, a natural solution. However, the question is whether they really exist. Unfortunately, the answer is not satisfactory. People do not know for sure. Though different multiverse models can help solve cosmological constant problem, currently no evidence shows they really exist beyond providing reasonable explanation for that strange coincidence. No evidence physical laws change with space, time, or between different quantum universes, only speculation. If other universes really exist, very likely they follow the same physical laws and same dark energy density value as our universe, bringing back to the original question. How can people exist when probability for this Milky Way formation is 1 in 10 to the 56, or worse, actual dark energy density smaller than theory prediction from 10 to the 56 to 10 to the 120th times? And finding evidence for that would be extremely difficult. People would have to survive a big crunch or travel to a universe region so far light cannot return or somehow step into another quantum universe, all seemingly impossible or at least extremely hard and possibly a one-way trip, like jumping into a black hole. This may forever be unprovable like God's existence, outside experimental science. Therefore, in a way, feel free to believe what brings peace, multiverse, design, or pure luck. Or perhaps continue waiting until humanity finds a better way to answer this question, with future technology. Ultimately, whether parallel universes with separate lives, space-time wormholes connecting distances, white holes erupting energy, or gravastars mimicking black holes, the theoretical picture of science is overflowing with endless possibilities, making everyone excited and humble before the vast universe, awaiting new discoveries to illuminate more of the darkness.